How's it going, y'all? Welcome to my lab report for Physics 2212 Lab 4, Bar Magnets. The purpose of this lab is to measure the distance dependence of a magnetic field caused by a bar magnet experimentally and computationally, then compare those findings. The materials in this lab include a bar magnet, meter sticks, tape, and a magnetometer phone app, along with glow script for the coding portion. The fundamental principles in this lab include the Biot-Savart law and the magnetic field of a dipole. The system is the bar magnet and Earth, while the surroundings include everything else. The first part of this experiment involved finding the distance from the magnet where the magnetic field was equal to specific amounts. This included orienting the phone to null out Earth's magnetic field, finding the location of the magnetometer on the phone and marking it with tape, and finally measuring the distance between the magnet and the marked magnetometer, where the field was equal to 20, 70, 120, 170, and 220 microteslas respectively. This was the data collected for each magnitude of magnetic field mentioned previously. The distance was averaged over 3 trials, and the data was then applied to a graph. In this graph, the line of best fit showed us an exponent of distance in relation to magnetic field. The slope of this line, about negative 2.53, represents the exponent of the distance in relation to the magnetic field, showing an inverse relationship between the distance and magnetic field. The y-intercept will be used to calculate the dipole moment on the next slide. Using the line of best fit from the last slide, the magnetic dipole moment was calculated to be about 7.91 ampere meters squared. This value will be inputted into the computational model to determine the computational magnetic fields generated by the bar magnet. The next part of the experiment involved finding the magnetic field off the axis of the dipole. This involved finding the perpendicular distance from the bar magnet where the net field was equal to about 100 microteslas. Then, using Pythagorean theorem, we found a location off axis and determined the net field at that location to be approximately 128 microteslas. This is the computational model of the experiment. As you can see, the magnetic dipole moment, labeled as μmag in the code, is implemented using the experimental data, as is dperp, the perpendicular distance for the off-axis calculation. The dipole field is calculated using the function dipole b above. Lastly, the arrows represent the magnitude and direction of the magnetic field at various points. On the parallel axis, the field points in the direction of the dipole moment, while on the perpendicular axis, the field points in the opposite direction of the magnetic dipole moment. I have circled some arrows on the model that are harder to see, but the two arrows at the top and bottom are also on the perpendicular axis, but further away, so their fields are significantly smaller in magnitude. Lastly, the circle slightly off to the top right is the off-field axis, which is pointing about 45 degrees up and to the right. This field is also quite small due to the distance between the magnet and that location. And as highlighted at the bottom, the magnitude of the off-axis magnetic field is calculated to be about 52 microteslas. As seen previously, there were several discrepancies between the experimental and computational data, mainly in the off-field axis calculations. This is due to several assumptions and potential sources of error. Assumptions in this experiment include assuming that the bar magnet acted as a magnetic dipole and ignoring the magnetic field generated by Earth in the computational model. Some sources of error include other surrounding objects creating a magnetic field such as electronics, along with the location of the magnetometer on the phone being imprecise. Lastly, there was likely human error when measuring distances or magnetic fields experimentally. What if I hadn't oriented the experiment to compensate for magnetic north, and had instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed? Because the net field now includes both the magnet and the Earth, the distances calculated in the experiment would have been skewed. Additionally, what if I stuck two identical magnets together and repeated the experiment? In that case, the direction of the magnetic field at any given point would remain the same, but the magnitude of the field would double as the magnetic moment dipole moment would double. Thank you very much for watching this lab report.